Ah, how do mathematicians do it? I mean, chucking this many characters into different equations, these long chains of logic, how can they fit all of that into their heads? Well, the answer is, they don't. That's because you don't need to memorize equations when you know what they mean. Oh wait, that's it. That's all the intro we'll get. Well, that's a bit short. Also, the title of this video is like the intuition behind equations. Who's gonna click on it? I mean, mate, I don't like clickbait, but we need to step up our game. At this rate, we're gonna go broke and... Oh! Hi there, hi. Right, video. So first we'll start with a warm-up. Right, a warm-up. That's definitely not because you caught me by surprise and I actually need to finish the big example. So first, oh, there we go. X plus y squared. What's up with that? Okay, so x plus y squared equals x squared plus 2xy plus y squared. What is up with that? Well, what's up with that is the fact that if we imagine a line with the length x plus y, then squaring it would be a square. That's where it gets its name from. It's squaring. Now we can see that x plus y squared is this square plus these two rectangles. All of these have their own corresponding part, or in other words, x times x plus xy plus xy plus y squared. So, hold on, why do we do it the square way? Like, don't get me wrong, it's pretty normal, but why go through all the trouble of drawing the square if we can just multiply them out? Well, that's because we can go even further. We can imagine a three-dimensional cube and we can ask, what does x plus y cubed equal to now? And we can decompose it into all of these different shapes. This kind of graphical representation can work not only for two variables, but even three or more. And the point here is that we could multiply it out, but this way of doing things is a lot more clearer, understandable and direct than this equation. Like, here you can see the reason for every single shape. Yeah, sure, maybe a bit overwhelming when looking at separate parts, but when we combine them all, it's really simple actually. If I show you just the letters, you're gonna flip out. If I go the graphical disassembly of the cube, however, it all makes perfect sense. You know where it comes from. So now it's time to play the devil's advocate. If this way of doing math is so great and all, why do we need to solve the equations at all? I mean, yeah, sure, math notation is optimized or whatever, but we could just as well use words, so why do we try to solve equations at all instead of just doing it graphically every single time? Well, it's because of abstraction. So basically, if we want to figure out the square with two numbers, easy. Cube with two numbers, easy. Cube with three numbers, easy. Hypercube with two numbers. Oh wait, how would I visualize a hypercube? I mean, here's the thing, there is nothing special about squares and cubes from a mathematical point of view. The only thing unique about them is that we evolved to interpret 3D world on a 2D plane. We've never evolved to optically process a 4D world, so whilst technically you could just apply the same method and just solve this equation with a hypercube, what's the point if no one can understand it anyway? That's why we usually just examine some sort of behavior, then we abstract it into something general, and that abstraction allows us to cross borders we normally wouldn't be able to cross, like the fourth dimensionality of a cube. And so with that brief introduction in mind, just to set the general vibe, we can get into the real examples. Oh wait, you're done already? Oh man, I specifically asked for a bloated example. Okay, it's fine, I got the rest of the video finished, so get ready for the absolutely amazing, mostly misunderstood and unbelievably complex, it's Max...
Can you make it?
Yeah?
Listen, next week I'll be making a video about quantum mechanics, and for that video I kinda need some math background, so... mind doing a quick segment on polar coordinates?
I mean, I kinda had a whole thing going and...
Ah, yeah, thanks. Bye!
Son of a... Okay, this isn't a maths history channel, so instead of going chronologically, I'll just go logically. The reason why is that you've entered the domain of my story, a realm in which I am omnipresent, omnipotent, and omniscient. A realm in which the very existence is at the whim of my mercy. A realm in which by all account and purposes I am a god! So right here I'm going to explain how polar coordinates work, and in order to explain that, we'll have to start with something understandable and yet really difficult to solve. Something like rotation. So first things first, if you have a point moving forward, you can just set its x coordinate, so left right, to the x number, y coordinate, so up and down, to the y number. And then describing the movement is really simple. Just add whatever number you want and there, it's moved forward. The problem, however, comes with the fact that if you'd like to rotate this point around a certain axis, then you're gonna struggle. This is a much more complex operation than just adding or even multiplying. Like, how would you even describe this rotation? Well, you could describe it using polar coordinates, so basically these coordinates tell you how far a point is from the origin and at what angle it is. Now, rotating the point with polar coordinates is easy peasy, because we can just increase the theta. There's really not much to it. The problem this time, however, comes in the fact that moving the point left and right becomes a massive pain. If only we could somehow switch between them at will, all our problems would be solved. If only there was a way for us to get the x and y for a given r and theta. Well, I guess there isn't one. Shame. I suppose from now on we'll just need to either move or rotate, not both, because, we can't just switch between them. Ah, what a shame. Make it? This is mathematics. If there is no way to do something, just make one. You do realize that everyone will hate the fact that you didn't say make it happen, right? So first we can break up our x and y coordinate into an x and y coordinate. Now we can see that from the perspective of either one of these coordinates, this isn't really rotation, it's more oscillation. Or to be more exact, right here it's oscillating left and right like a cosine, and right here it's oscillating up and down like a sine. So we can see that if we'd like to rotate a point around the origin, this would mean the x-coordinate being the cosine of that angle, and the y-coordinate being the sine of that angle. Now if we switch to a Cartesian vector, we can see that the point is rotating. Now if we multiply both these by an r, we can see that this point moves further or closer. So that's what conversion from polar to Cartesian means. It's basically us converting the angle and distance in the y direction and x direction separately. But what about converting back? Well, now that we've got the coordinates, there are two things we'd like to know. First of all, the distance. Second, the angle. The distance is simple, a Pythagorean will suffice, and for the angle, well, you could pick theoretically any trigonometric function, but tangent is the standard since it depends only on the x and y coordinate directly. And actually, that's it for converting between them. I could also go into how different transforms work with different coordinate systems, but for that I'll have to explain the Eulers identity and formula, and it's just a whole thing, so I'm just gonna skip it. Alright. And okay, the polar coordinates explained, you're welcome. Now we can finally get into the actual equation that I've prepared for this video, and it's a pretty big one, so get ready for the— No, make it! I'm you from the future! Oh great, another one. What is it now? You've explained the conversion without the Eulers formula, and for that you're going to die! Well, I mean, that's a bit of an overreaction, did you think? I mean, killed just for not mentioning something in a YouTube video? That does seem a bit— Also, people will unsubscribe from you on Patreon. What?! That's madness! Quick, we need to explain it! So first, let's start simple enough. What is Euler's formula? Well, it basically states that Re to the power of I theta is equal to R cosine theta plus Ri sine theta. Okay, so simple equation, no worries, I can just knock it down like an hour or something. Let me just quickly check why that is exactly, and— Wait. You mean to tell me that it's complex numbers, exponential factorials, infinite sums, and all that just for the power? Huh. Oh, whoops, I forgot to take my schizophrenic pills. Alright, so first we have sequences, defined as an A of n is equal to, and an equation with n. So for example, a sequence with just plain n will look like this. A sequence of n factorial would look like this, and a sequence of n to the third power divided by n factorial would look like this. So these are sequences. They're pretty simple enough, but we can complicate them by turning them into a series. Basically, if you imagine a sequence like an is equal to 1/2 to the nth power, then that's, well, a pretty simple one. But you can turn it into a series by just adding them together. So what would that mean, for example? Well, imagine a line of length 1. The first element of our sequence would be kind of like the half of our line. Then the second one would be like the remaining half, halved. Then the third one would be like the remaining halved, halved, and we just keep going. You can see that as we go on we add more and more halves until eventually we would reach the full line. Now what is the number of segments at which we would reach the full line? 100? 1000? Well, not quite, it would be more like infinity. That's why we call it an infinite series. And so that's why an infinite series of 1/2 to the nth power is equal to 1. Right? No! Wrong! In math and science in general, you can't just say that things are a certain way just because they look to be a certain way. You need proof. So how would we prove this? Well, think of it this way. For n equals 1, we get 1/2. For n equals 2, we get 1/2 plus 1/4. Or in other words, 2/4 plus 1/4, so 3/4. For n equals 3, we get 1/2 plus 1/4 plus 1/8. Or in other words, 4/8 plus 2/8 plus 1/8. So 7/8. And that's enough for us to analyze it. You see, this way, with each greater number, we end up with a greater number in a denominator. That's because we always take the denominator of the last number, and the denominator of the last number is literally just 2n. So we already know that our result will be divided by 2 to the power of n. But what about the numerator? Well, each time we increase the n, we multiply the entire numerator by 2, just like the denominator. So it would also be 2 to the nth power. Except from the start, we're missing 1. Now, because this is exponential, the gap between two numbers would just get bigger and bigger and bigger, if not for the fact that each time we're also adding 1, so we're not letting it grow any bigger. And so we start with the gap being equal to 1, then on each step we multiply by 2 and add 1, multiply by 2 and add 1, multiply by 2, add 1, and I could keep going because this is just the single animation just looped over and over again, so I can just keep adding it in the Premiere. And so we end up with the final equation for our series, 2 to the nth power minus 1 divided by 2 to the nth power. So, what will our series equal to if we plug in infinity? Well, that's simple. We shouldn't actually plug in infinity, it's a bad practice and mathematicians will give you the funny look, so instead we'll just do it the proper way. A limit as n approaches infinity. If we take the 2 to the n by 2 to the nth out, then we get this. 1 minus 1 divided by 2 to the nth. 1 divided by 2 to the nth will eventually go to 0 as n approaches infinity, and so we get 1 minus 0. Or just 1 if you're feeling zerophobic. And so now the point is, that's how series work, and that's how we can analyze them, and with these series we can do something rather fun. So, imagine a function. Any old function would do, a solid f of x, if you will. Now we don't know what the f of x is equal to, but what we do know is its derivatives at 0. What are derivatives? Well, I've actually already explained it before in the most popular video on the channel, but basically they tell you how the function is changing. So the 0 derivative tells you just where the point is, the first one where it's going, second derivative tells you the curvature, and so on and so forth. Now let's just say that we don't know f of x, it's just any old function, we don't know it, but we do know all the derivatives at 0. Is there a way for us to construct a function that would approximate f of x using only these derivatives? Well, there is, and that's with polynomials. So basically, if you have 5 derivatives, how would you construct the polynomial? Well, you can start with the derivative number 5. If we evaluate it at 0, we get the 5th derivative at 0. Right here, I'm just gonna represent it by d5 for the sake of simplicity. Now, if we integrate our derivative, we'll get the 4th derivative on the left side, because integration is anti-derivation. But what about the right side? Well, on the right, following the rules of integration, we'll get d5 x plus c. But since we do know all the derivatives evaluated at 0, we also know that this equals to d4. And the real kicker comes in the fact that since we know that we evaluate this at 0, we can make our own little side equation like this. d5 x plus c equals d4 with x equals 0. Or in other words, c equals d4. So the 4th derivative at 0 will be d5 x plus d4. And so then, with that in mind, we can carry on and integrate again to get the third derivative. Once again, rules of integration: d5 x squared divided by 2 plus d4 x plus d3. Each time we're basically multiplying each of these derivatives by x, and we divide each of them by the power of our x. And as simple as these rules may seem, that really is how you integrate. So for example, for the second derivative, we take our previous derivative, multiply each of them by x, we divide each of them by the power of x. Right here, x is to the first power, so we don't quite care. This could be divided by 1, but you know, it's just simpler this way. And we add a new derivative. Then we keep going, and there we go! We've reached the original equation. And you can see that since for each step we've multiplied by x and divided by the new number, that's equivalent to us bringing the x to the derivative's power and dividing by a factorial of that power. Now I know that it might have been a lot, so let's replay what just happened, this time from a perspective of a single derivative. We start with that derivative. We multiply it by x and divide it by 1. We multiply it by a second x and divide it by 2. Third x, divide by 3. Fourth x, divide by 4. Fifth x, divide by 5, and there we've reached the same order as the derivative. So I hope you understand how we got here to the full sum. It's just multiplying by x, dividing, and adding another term each time for all of these separate terms. And the thing is, you could just keep going, increasing the amount of derivatives to eventually create an infinite sum, the Taylor series. So the basic job of a Taylor series is that for most functions, it's just equal to the function itself. So it gives you the power, among other things, to rewrite functions as sums. Why is this important? Well, it's because you might have noticed something about our little animation. I did not include any actual function to visualize. All of this was just on some general arbitrary function f of x, meaning that we could just apply it to a bunch of different functions. So let's start with something simple like e to the x. Why would we care about e to the x? Well, for the obvious reason, it's its own derivative. That's why the derivative of e to the x is e to the x. Obviously, why else would we care about that? So the e to the x at point 0 will be equal to 1 for every single derivative. And right here you have the Taylor series for e to the x. You can see that it's really simple because, well, we just replace all the derivatives with 1. It really doesn't get simpler than that. You can also do something a tad more complex, like the derivative of sine. Sine is perfect because whilst it is more complex, we're still only dealing with fixed point numbers. The derivative of sine is cosine, which derivative is negative sine, and then repeat, and so on and so forth. It's just oscillating 0, -1, 0, 1, 0, and so on and so forth. So it's the same series except every second x disappears, because we multiplied by 0, and every fourth switches to a negative, like this. So here we have the Taylor series for sine. What about cosine? Well, cosine is just the derivative of sine, so we can just offset everything by 1, and there we go. Those are the Taylor series for the trig functions. But you know what? Let's just do one more good one. So do something a bit more complex, you know, like e to the x. Actually, no, more complex, or e to the ix. I know, I'm hilarious. So Taylor series of e to the ix is just like e to the x, except with the notable difference that every one of the 4 is multiplied by I. Second of the 4 is multiplied by -1, third one of the 4 is multiplied by -I, and fourth is just multiplied by a 1. The reason being that we basically also multiply each of them by I to a certain power, but I to the power of 1 is I to the power of 2 is -1, I to the power of 3 is I to the power of 4 is 1, I to the power of 5 is I, and then go over in cycles once again. Now at this point I think you may be pretty well acquainted with the Taylor series, and skipping over the extremely important, especially in this case, but, well, in all honesty, kind of boring radius of convergence, I think you can understand how they work, and so now we can finally have some fun with them. So for example, we can take the complex exponent of e and we can separate it into the real part and the imaginary part. And so now you can see that, hold on, This kind of looks like a Taylor series. Like 2 separate Taylor series. So, hold on, let me check my ancient tome of wisdom. Yes, there we go. It's the cosine. And the other one is... it's the sine. Or in other words, e to the ix is equal to cosine of x plus I sine of x. The Eulers formula. Now yes, we can multiply both sides by r and get the polar coordinates, and now that we've got here, there's only one last thing to mention. That is, what does this mean? I mean, yeah, sure, we've gone over the Taylor series, but why haven't I gone with the natural log side? Look at that beautiful spiral. Well, it's because you should already understand the intuition behind the Eulers formula. It's the polar coordinates. My point here is that behind almost all of math there are 2 sides. The intuitive side and the rigorous side. The intuitive side makes it understandable. Like for example, in our case, the polar coordinates. You understand why the rotation happens if you get the Eulers formula. But the rigorous side can't be forgotten. Without the actual proof, the equation is meaningless. And so just like with the very beginning, we started with something understandable, then we used abstraction to skip over the complex, and then we got back the proof of the understandable. And so that's the 2 sides of math, the intuitive and the abstract, and neither can be forgotten about. Unless both sides are the same side, and you can prove it in a way that's both understandable and rigorous, but that's a story for another time. Alright, there we go, that was Eulers formula, finally explained. Certainly took a while, because I have used it in my videos before, and it feels good to finally get it off my chest, you know, explaining with the Taylor series. But yeah, that was just a temporary chapter. Now we can finally get to the meat and potatoes. Now we can finally get in... Usually right about now there's a MAKiT from the future interrupting, or like something happening. No, nothing? No silly gimmicks? No bits, no jokes? Alright, I guess that really must be it this time. No more interruptions, no more anything. It's finally time to explain the Maxwell's Oh, would you look at that? That's my alarm. You see, recently I've started doing YouTube full time, but since my videos aren't all that popular, this means that I need to make at least 1 video a week. So, well, I guess that will be it for this one. I guess that's all the time I had. I would like to finish this video by specifically thanking Kuaza and Alm. Kuaza for becoming the highest tier patron, and Alm for drawing this absolutely lovely fan art, which is really lovely, and I do love it. I hope I didn't mispronounce your name. And also you, Legbear. Haha, I thought I'd forgotten about you. Well, I have not. Thank you all so much for this. I really can't stress enough how much I appreciate your help. I am going through a bit of a, well, tough time, let's just call it, because even though I have savings, I'm not going homeless anytime soon. This isn't really sustainable, so this is what my fridge looked like. But don't worry, that was on stream. After the stream I went grocery shopping, and now it looks like this. So I'm pretty much all set. Thank you everyone so much for help. So yeah, I have Patreon if you'd like to support me. I also have a Discord server if you'd like to chat with me. And also I stream every single day for charity, a series of live streams called Charity Checkups, which I would really recommend you join in. Anyway, I suppose for now be it. I have not explained nearly enough. I thought I would explain more this video, but I haven't exactly got the time, so I guess we'll have to leave that for the next math video. Thank you everyone so much for watching, and have a great day. Bye.